So today I would like to speak you about a joint work with Simone Ciani, which is actually a PhD student at the University of Florence. And it involves the contact surface of Cheeger sets. Okay, so let me immediately introduce you the ingredient of the dissertation. So the Cheeger constant is a variational quantity and is defined as the following infimum problem. So you minimize among all subset of a given open subset omega, the ratio between the perimeter of E and the Lebesgue measure of E. Actually, the perimeter of E is more the distributional perimeter, which can be thought for now to be just a d-1 dimensional surface of the boundary for regular sets, or the surface measure of the boundary for regular sets. Now, what is a Cheeger set then? A Cheeger set is any set which attains this minimum. So any set for which the ratio between the perimeter and the Lebesgue measure is equal to H is called a Cheeger set of, or sometimes even for, omega. Okay, this object was introduced by Jeff Cheeger in 1970s to bound from below the first eigenvalue of the P Laplacian, the first Dirichlet eigenvalue of the P Laplacian. And indeed, this inequality is always in force, you can see, for all P bigger than 1. And you can also show that, in some sense, the Cheeger constant really represents the first eigenvalue of the 1 Laplacian in some sense. Because if you take the limit as P going to 1, you recover the Cheeger constant. Okay, so it's a geometric quantity now. It's no more have to do with eigenfunctions. So we look to this ratio and we want to minimize this ratio. Just to let you understand what are we talking about, here is immediately one example of an ambient space omega, the dark one, so the container, and the red one is the Cheeger set. So I will denote contact surface of Cheeger sets as the part of the boundary of the Cheeger set which sticks to the boundary of omega. So the part which remains adherent to the boundary of the container. While instead the interior part, this one here, I don't know, I think you can see my mouse. I think so.
Yeah, we can.
Okay, so the interior boundary is called free boundary. Okay, as you can see from this example, the Cheeger set is trying to be big. So in this particular example, is invading almost all the space. So it doesn't leave too much empty space, just around corners. But there can be situations where, you know, things aren't that nice. For instance, if you have steep angles like this, there might be the case that the Cheeger set doesn't want to enter too much. And so it creates a bigger empty region. The reason is because basically, okay, the ratio between perimeter and volume is a bit unbalanced in favor of the volume. So it's a little bit more convenient to be big than to be small, but up to some limit because you have still the perimeter at the numerator. So for instance, if the Cheeger set tries to enter too much in this angle, he's going to pay a lot of perimeter, way more than what the area increasement can compensate. Okay? And there can also be situations where you don't have angles, like in this case, where the Cheeger set actually occupies all the space he has. So the boundary of the Cheeger set is completely adherent to the boundary of omega. Okay, important remark that I thought was a good point to place. In this case, we are looking at the ball, and as you can see, the Cheeger set of the ball here is the ball itself. Now, the only set which has this property is the ball, in the sense that if you know that the Cheeger set of something is a ball, then this something has to be a ball as well. Okay, so in other words, the ball is the only set which has a Cheeger set, which is the ball itself. okay? This is not the only case, though, where the Cheeger set is adherent to the boundary completely. Okay, there might be other scenario, but the case where the Cheeger set is a ball is a particular characteristic of the ball. Okay, so I've been showing you some example to set the definition of contact surface and Cheeger set. Now, let me show you what is the plan of the talk for the next slides. So, in the next few slides, I would like to introduce you some known properties of Cheeger sets. Okay, the literature on Cheeger set and Cheeger constant, it's quite vast. So I've been selecting some properties which are useful to the argument we will develop. So it's more a selected list of properties of Cheeger sets. And then we will later focus on the contact surface. In particular, we would like to understand how small or how big it can be if there can be given a bound on the sides of the contact surface. You'll see that there is an easy bound. For instance, it cannot be empty. So the Cheeger set will have to somehow touch the boundary somewhere, at least in one point. But you can say something more. So you can give explicit lower bound on the dimension of the contact surface, on the Hausdorff dimension of the contact surface. Now, since this lower bound will be a bit cryptic, I think that a sketch of the proof will clarify where this bound comes from. And the nice thing is that the proof relies on instruments which are imported from the theory of removable singularities. And finally, I would like to show you examples that somehow show that the bound we've been giving in section 2 are sharp. So we will build sets that will saturate those bounds. Okay, so let's immediately start with the existence and interior regularity property. A very easy property is that given a bounded open set omega in Rd, then you can find at least one Cheeger set. Okay, this is just direct method of calculus of variation and lower semi-continuity of the functional understudy. Moreover, there is an interesting interior regularity, which tells you that the free boundary, so the part of the boundary of E which lives inside the container, is actually an analytic hypersurface with constant mean curvature, and you can know what is the constant because it's actually the Cheeger constant. So the free boundary is a very rigid shape. Okay, let me draw your attention on these two over here. So this assertion in this version is true in dimension 2. I've decided to state it in dimension 2. This is actually true, the regularity, the interior regularity and the existence, of course, is true in every dimension. But a technical small issue arises if the dimension is too big. For instance, if the dimension of the ambient space Rd is bigger than 8, then the second statement is true, but up to a small singular set sigma, which has Hausdorff measure small, not bigger than d-8. So to avoid these technicalities, I decided to present the regularity properties mentioned too. But you should remember that these statements are true also in bigger dimension. Just with this minor correction on the second property, which includes to take into account this possible singular set which arise. Okay, so you have the interior regularity. You can also hook up a boundary regularity. So if you have an omega bounded open set in R2, then the first boundary regularity that you can state concerns the way in which the free boundary meets the boundary of the ambient space. So what happens is that if omega is regular enough, then the free boundary can meet the boundary of the ambient space only in a tangential way. So not orthogonally, not with an angle, but really tangential. Which means in particular that if you look at the outer unit normal of the Cheeger set, it will become parallel to the outer unit normal of the ambient space in the contact point. Moreover, you have some additional mild regularity on the boundary of the Cheeger set around contact point. So you can infer that if the boundary of the ambient space is C1, then the boundary of E has to be C1 as well in a neighborhood of the contact point. And also C11 can be transferred to the boundary of E. Finally, you can see that if omega is convex, then you can also claim uniqueness of Cheeger set. And also a C11 regularity of the boundary can be inferred around contact points. So in picture, this means the following. So you have a free boundary part in here, which has constant mean curvature, which in the plane means just is a circular arc of radius 1 over h. Then you have a contact point. So as you can see, this is a contact point where the free boundary meets the boundary of the ambient space, and it can meet it only tangentially. Moreover, around this point, the function stays C1. Okay, this is meaningful because far away here, where you have that the boundary of the Cheeger set is completely adherent to the boundary of omega, you have the same regularity of omega. Here you have the regularity of a constant mean curvature hypersurface, which is infinity. So this implication is actually telling you that the C1 regularity is preserved also around this small point. And also the C11 as well. Okay, so now this is a list of selected properties, as I said, and you look at this list and then you look also to the example, and you feel like that there is a desirable property which seems to be missing and you would like to get, which is basically this one here. So in all this example, it seems that the boundary of the Cheeger set is sticking to the boundary of the ambient space on sets with d-1 Hausdorff dimension. So basically the surface contact has really d-1 dimension. Okay, so you wonder if this can happen in some cases. But then you think about it a little bit and you can cook up this guy. Now this guy has a free boundary which is constant mean curvature hypersurface or a circular arc in the plane. Then the boundary of omega is Lipschitz, so it's quite innocent. But the Cheeger set and the ambient space share just these 6 points. So the contact surface here is made by 6 points. So you have to add these to the list of your examples. And well, exactly as I said, in general, you conclude that this property will hold in some cases, not always. So the main idea now is trying to understand in which cases this property arise and if additional bounds can be given. So this will be the topic of the next slide. Okay, the first remark is that you cannot be too small, as I said. Okay, there is an easy bound. So for instance, you cannot be empty because you have this ratio between the perimeter and the volume, which tends to be in favor of the volume. So if for instance, the contact surface is empty, as in this case, so this is just a fancy way of saying that the cardinality of the intersection is 0. So there is no point in the intersection. Now what you can do, you can dilate this set a little bit. So pretend that E is a Cheeger set. Then you dilate it a little bit until it touches the boundary, for instance. If this lambda is bigger than 1, then you can take advantage of this scaling to decrease the Cheeger constant, which is impossible because this was the minimizer. So you get a contradiction, which means that the cardinality of the intersection needs to be at least 1. Okay. Not a big bound, but at least it's something. You can push this a little bit more by saying that actually it has to be at least 2, because if it's just 1, let's think just in the plane for now. If it's just 1, then you can translate the Cheeger set inside your ambient space a little bit without exiting. And of course, the ratio between perimeter and volume will not see this translation. So by doing this, you will build a Cheeger set with 0 contact point and still being a Cheeger set. So you are back in the previous scenario, basically. And this gives you another contradiction. So particular, you can say that the intersection between the boundary is at least 2. Okay, you can probably push this a little bit further, but it's kind of clear that at some point this argument will break. You won't get much more than H naught, okay? So, okay, now I'll give you the statement we had with Simone, which gives bounds on the Hausdorff dimension of the contact surface. So recall this example, we just proved that this has to be true. What actually is true is that the sides of the contact surface is linked to the regularity of the boundary of omega, which is kind of expectable. And the quantitative bounds can be stated in this way. So if boundary of omega is regularity of class C1 alpha for some alpha in 0, 1, then the d minus 2 plus alpha dimensional Hausdorff measure of the intersection has to be positive. And this holds for any of the Cheeger set omega. Okay, so this is a stronger assertion that you can get if alpha is 0. And okay, in particular, if alpha is 1, so for domain omega with boundary regularity of class C1, 1, it means that the boundary of E intersected with the boundary of omega has actually sides d minus 1. So one answer to the previous question is that hd minus 1 of the contact surface is positive if the domain has boundary of class C1, 1. What actually happens is that these are sharp bounds, because in the plane at least, for any alpha in 0, 1, you can cook up example in which these bounds, in which this Hausdorff measure is positive exactly at size alpha. So in particular, it means that this object will have Hausdorff dimension of size alpha. So in particular, whenever you try to measure it with HS, when S is bigger than alpha, you don't see it. And you see it just at size alpha. Okay. So brief clarification about Hausdorff measure that I will be using later. So the Hausdorff measure sees objects of its own dimension. So HD minus 1, it's positive on objects which are roughly d minus 1 dimensional. So as well as H1, for instance, in RD can see curves, H2 can see planes. The nice thing about Hausdorff measure is that it can see also fractal dimensions. So not integer dimensions, let's say. So HS for S between 0 and 1, it makes sense. And indeed, just fractals dimension can be caught by HS somehow. So what's happening here is that since this example can be cooked, one consequence is that this object will have a fractal behavior somehow. So it will have non-integer dimensional, Hausdorff dimension. Okay, as I said, these bounds are cryptic. In particular, why this alpha is moving from here to here. So let me give you the strategy of the proof. And I hope that it will clarify why there is this, this trade-off in regularity and size. So the more regular it's the boundary, the bigger can be this, the bigger has to be the contact surface. Okay. Just a first warning before going on is that these bounds are actually a global bound. So locally, this statement is false. So in particular, if you look at this example, for instance, you have that the contact surface here is t minus 1 dimensional, because it's, well, it's one dimensional, let's say it's in the plane. But you can cook up this other guy here without changing the Cheeger constant. So you can deform locally omega into this omega tilde until it touches the boundary of E. Now, from the definition of Cheeger constant, you can see that this kind of deformation doesn't change the Cheeger constant. In particular, if this guy here was a Cheeger set for this omega, after this deformation, it remains a Cheeger set also of omega tilde. But now the contact surface has gained these additional points. So globally, the dimension of the contact surface here, it's still d minus 1. It's still 1. But if you go local, here you have that the contact surface is made by finite number of points. So what I mean is that these bounds are global bounds. So you cannot localize them to some portion. Okay? So this also means that whatever argument we will use to prove these bounds, we'll have to take into account the global structure, not just, it cannot rely too much on local principles. Okay. So let's start with the strategy of the proof. So the first thing you do is that you assume that omega is not a ball. And the reason it's equal. If omega is a ball, then the contact surface is the full boundary of omega. So the bounds are trivial. So you have immediate the bounds you want. So you can, without loss of generality, assume that omega is not a ball. And this is a very important point. Then you then you localize yourself and you pick a point in the intersection. You take the graph representation. So Fe represents the boundary of E and F omega represents the boundary of omega. And then you start to observe that there is something going on here because this is part of the free boundary. Okay, these two are the same graph one. This is just a little bit zoomed. Okay, this is part of the free boundary because it came from here. And we know that the free boundary has constant mean curvature. So if it has constant mean curvature, it means that on this portion here, the graph, the function Fe will have to solve the constant mean curvature equation. So in particular, if you restrict yourself to d minus gamma, then Fe will solve this equation, where the constant is exactly h of omega. Now, if you call now small gamma to be the pre-image, basically, of the contact surface here, then this means that these are exactly the point where this equation fails, right? So you can say that if gamma is the pre-image, which, important thing, has the same dimension. So this is one-dimensional in this case. And if you go back, it stays one-dimensional. So it's a full measure. It's a set of positive measure in R1. So it means that it has positive H1 measure, like this guy. So what's going on is that if you localize yourself around the contact point, you can identify a portion where your function Fe satisfies the constant mean curvature equation, and the portion where the constant mean curvature equation might fail because it's where it's sticking to the boundary. Okay, now, if this is the situation, you can actually go on with any kind of argument. The reason is that in this case, gamma is already big, in the sense that it's d minus 1 dimensional. So you should be already happy with that, because we are interested in the case when this is small. So we would like to rule out the fact that this guy is small. So this small gamma or this contact surface is small. So what happens if we are in this situation? So let's forget for 1 second the figure, the upper figure. And let's observe that now, suppose we are somewhere in a point where the graph representation has precisely this structure. So we have a free boundary on the left, a free boundary on the right, and now you have just one point as a contact surface. Now you still can write this because outside of d minus gamma, still you have constant mean curvature here and here. But now gamma is a point. And if, for instance, you know that omega is C1, then the regularity of omega and the fact that this boundary has to meet tangentially the boundary of omega is kind of forcing this point also to solve the constant mean curvature equation. So if you think well for 1 second to this scenario, if this is the case and if gamma is just one point, then what you are telling me is that Fe is actually solving the constant mean curvature equation on the full domain. Okay, so if gamma is big, I'm good. If gamma is too small, I can now run a strategy, because if gamma is too small and I localize myself, I see the constant mean curvature equation up to a set gamma. But if gamma is small, now I remove the set gamma. So I see the constant mean curvature equation on the full D. Now imagine now the principle is basic this, and we will enter in it also in next slide. Imagine now that you repeat this argument on every contact point. So what you should conclude is that the constant mean curvature equation holds around any contact point. And then you have also that the constant mean curvature condition holds in the free boundary. So if you collect together this information, you are left with a closed surface which have constant mean curvature. So it has to be a ball. So omega will be a ball, and so you are contradicting this assumption. So the strategy now, in particular, this means that understanding the removability of this gamma is giving us a weapon to attack this problem. So let's recap. Suppose that you have that gamma is small enough, so you can guarantee that whenever you have a solution to this equation, then it's actually a solution also to this equation. It's a bit vague, but we will become a bit precise later. As I said, now you repeat this argument around because this is telling you that the boundary of E has constant mean curvature in the small cube where you are looking at the graph representation. Now, if you assume that the full contact boundary is small, whenever you place yourself locally, you see that the small gamma, which is just the pre-image according to the graph representation, will still be small enough to be removed. This small enough will be quantified. And so you can repeat this argument on any contact point. And so you have that the free boundary has mean curvature, constant, and the contact surface also have neighborhoods in which the boundary of E has constant mean curvature. So you couple these two, and as I said, you get that boundary of E is a Napier surface. So you have to claim Alexandrov's theorem here, and then conclude that E is a ball. Okay, just a brief digression on a small technical point. You will get these up to a small set sigma. So you don't get that the boundary of E is in a hypersurface with constant mean curvature, analytic, closed, and C2 without boundaries, so that you can immediately claim Alexandrov's theorem. You almost get what you need. So you need this instrument here, which is kind of crucial because it's a refined version of Alexandrov's theorem, which allows you to still conclude that E is a ball without caring of this small set. Okay, just to give you this small technicality. Okay, so the sum of the argument boils down to the following thing. If this is small enough, then it has to be a ball. But the ball can be a Cheeger set only of the ball, as I said. So omega is a ball, period. And you have a contradiction. So this means that to rule out the contradiction, this guy cannot be small. And how big it has to be? It has to be at least as big as it is required so that this remotion cannot be performed. So basically we will look for the biggest sides for which this remotion can occur, or if you want, for the smallest sides for which this remotion cannot occur anymore. Okay, so we will study, and that's where removable singularities kicks in. Okay, brief remark, trivial observation. The removability of gamma depends clearly on the information you have on the U. So the more regular the U is on the full D, the bigger gamma can be. Until you get to the extreme scenario, for instance, if you know that U is C2 on the whole D, and it solves the constant mean curvature equation on D minus gamma, then by continuity of the derivative, basically any set with Lebesgue measure 0 in its own ambient space is removable. Okay, this dimensional observation is important because we are looking here at graphs. So our function goes from Rd minus 1 into R. So Hd minus 1 of gamma equals 0, it means that gamma has 0 Lebesgue measure in its own ambient space. Okay, so it can be quite big, but U has to be quite regular. Okay. Okay, so the problem is that we cannot rely to such regularity. We can hope just to have C11. So we cannot just invoke the continuity of the derivative and conclude. So we need to dig deep into this concept of removable singularity, which can be basically stated, actually the question can be posed in general in this form. So if you have a solution U which solves LU equals 0, where L is a generic elliptic operators, and you know that it solves it on D minus gamma, when can you conclude also that LU is, that U solves the PD on D? So what kind of condition you have to impose on gamma? And as I say, this is going to depend on the regularity and also on the size. Okay, below here, you can find a very partial list of the literature on the topics of removable singularity. These two works of Serrin were one of the milestones that started, they introduced this topic. We will refer in the next slide to this theorem from De Giorgi Stampacchia, later improved by Simon, okay? To try to understand what is going on. So, this theorem concerns in particular the constant mean curvature equation. So it seems to be suited to our situation. And it's very powerful because it's not exploiting anything but the equation. Okay, the fact that U is C2, but this is a consequence of the equation almost. So this theorem tells you that if you have a function U, which is C2 on D minus gamma, now D is contained in RD prime, because since I have this graph representation, I will have to move from D to D minus 1. And so for the sake of clarity, I just set here D prime to be D minus 1. So, but it's fine. I mean, this is actually true in all the dimensions. In particular, you can rename the dimension. So this theorem tells you that if you have a C2 function on D minus gamma, which solves pointwisely the constant mean curvature equation outside of gamma, and if gamma is negligible with respect to D prime minus 1 Hausdorff dimensional measure, then you can extend U to a U tilde, which is C2 everywhere, and that solves the constant mean curvature equation. Okay, this is quite powerful. So let's see what kind of bounds can we derive by implementing this theorem. So let's run the whole machinery with the De Giorgi Stampacchia Simon theorem for removable singularities. So we start, as said, by contradiction. We assume first that omega is not a ball. Second, that the contact surface is small, quantitatively small in the sense that HD minus 2 of the intersection is 0. But okay, for the sake of simplicity, we suppose boundary of omega C1, right, just for now. Then we pick a point in the intersection. Okay, we set D prime, as I say, to be D minus 1, so we forget almost that we change the dimension. Then you represent the intersection of the boundary with the graph. And so you identify the part of the domain in RD minus 1 or in RD prime that maps to the contact surface. So this gamma encodes the point below, which will be mapped up. So it's the blue part I've shown you before. Now, standard geometric measure theory argument tells you that if this is small in this sense, then this guy will be small in this sense here, because you can bound this dimension with the dimension of the, basically of this guy, which is diffeomorphic to this guy, kind of. So this was 0, so you're good to go. Remember that D minus 1 was equal to D prime. Now we are in good shape because we have that gamma has the right sides. The constant mean curvature equation is satisfied outside of gamma. The function goes from RD prime into R because it's fine. So we invoke the Giorgi Stampacchia theorem and we remove this gamma. So we are left with the full equation. So we now go on by means of Alexandrov theorem revised, and we conclude that D is a ball. So omega is a ball, and so we have a contradiction. So the contradiction can arise to avoid the contradiction, basically, either omega was not a ball from the very beginning, or this has to be false. Sorry, or either omega was a ball from the very beginning, or this has to be false. This has to be false. So this has to be true. So either omega is a ball, or the contact surface has these sides. So we just provide ourselves with this bound, which is telling us that the contact surface has at least d minus 2 Hausdorff dimension, which is still not d minus 2 plus alpha. So I still miss the plus alpha. So the De Giorgi-Stampacchia-Simon theorem, it's not giving me the full bound. Okay, the reason is that because basically the De Giorgi-Stampacchia-Simon theory, it's very powerful, but it does not employ any regularity of the function u. So it's somehow the best result you can attain without knowing anything but the equation. But if you dig deeper, then these results pops out, which is a Pokrovsky's theorem, which is telling you that if you allow yourself to know something more on the function, for instance, that the function is also C1 alpha outside, in gamma basically, so it's C1 alpha on the full D, then you can increase the set, the sides of the set which is removable up to d prime minus 1 plus alpha. Okay? So as you can see, if you remove the red part, you get the Giorgi-Stampacchia-Simon theorem. If you add this is a trade-off, because you are allowing yourself to have some more regularity, so you are using more information. And you transform this information into a bigger set that can be removed. Okay, so Pokrovsky developed this result first for the constant mean curvature equation with h equal to 0, then with the P-Laplacian equation, and then lately for uniformly elliptic equation in divergence form. And they are very interesting paper. They are listed here. So somehow, whenever you have an equation in divergence form, you can invoke this principle. You can say that satisfying the equation and being C1 alpha allows you to remove sets whose size is d prime minus 1 plus alpha, negligible. Okay, before go on, let me underline the following observation, because this kind of appears that the structure of quasi-linear elliptic equation is not really required to do the Pokrovsky's theorem, in the sense that it turns out that this is a property of the divergence, of the distributional divergence, in the following sense. If you have a vector field F, which is C alpha, and you know that the distributional divergence of F is G on D minus gamma with some regularity on G, mild, then you can extend the distributional divergence to the full set, provided the set where you don't have information has sides D prime minus 1 plus alpha negligible. Okay, so this kind of explaining why all the equation with divergence form are suited for this remotion argument somehow. So this is something we observed with Simone. I thought it was interesting to be reported, but it's not the main topic. So let's invoke now Pokrovsky's theorem, and let's run the argument before with this new improved singularity remotion argument. So we do as well as before. We start from omega, which is not a ball. We assume that this is small now in this bigger sense. So hd minus 2 plus alpha of the intersection is 0. And you assume that the boundary is C1 alpha. Now this is important. Now you pick a point and you rename d prime, okay. As well as before, you define gamma to be basically the diffeomorphic image of the intersection of the boundaries according to the diffeomorphism induced by Fe. Let's forget for 1 second A1. B tells you easily that as before, since this was small, in particular this measure was 0, the measure of this guy was 0, you can transfer this smallness to gamma with this equality, basically. So this was 0, implies that gamma has to be negligible in its own dimension. Then you observe that, as before, the constant mean curvature equation is satisfied on d minus gamma. The singular set has the right sides. Now, Pokrovsky's theorem, recall that requires this condition because it's the whole point. You need to be more regular so to enlarge this guy. So to get this condition, we need to go back at the point A1 and somehow observe that if the boundary of the ambient space is regular, then you can transfer this regularity also to the boundary of E. So if boundary of omega is C1 alpha, then you need to prove that this implies that the boundary of E is C1 alpha. You have at least to prove this, right? This is true for alpha equals 0, as I shown you in the beginning. It's true for alpha equal 1. And with Simone, we filled the lack by proving this for all alpha between 0 and 1. We couldn't find it in literature, so to the best of our knowledge, at least. So once you've done A1, you observe the inequality in B, you write down this condition, then you invoke Pokrovsky's theorem, because you have all the ingredients. And then, as before, this gives you constant mean curvature equation on the full D, which gives you boundary of E as constant mean curvature equal to H around contact point, which coupled with the information that the boundary of E has constant mean curvature also in the part which is the free boundary, tells you that E is a ball. And you get a contradiction. So either omega is a ball or this is big. So if omega was not a ball from the very beginning, then this means that this bound has to be true. Okay, so we got the bounds. Okay, now the case alpha equals 0, which I've been omitting from the presentation, is actually allows you to get a better estimate here. So you can also say that if alpha is 0, this is not only positive, but it's plus infinity. And this has to deal still with the fact that you can get a bigger size for removability explicitly for alpha equal to 0, which is bigger than just d minus 2 plus alpha equals 0. Okay, but I don't want to enter in that. Okay, so final part. I think I still have the time to show you briefly the sharp examples. The last part is now I would like to show you that we can cook up examples in which these bounds are actually saturated. In particular, I will build for any alpha an open bounded set which is regular. The regularity is actually C1 alpha, and such that the Hausdorff dimension of the contact surface is actually alpha. So it's going to look fractal, to look like a fractal. Okay, so how do you build such a thing? We have to go back to the way we proved the bounds. So we relied on tools from removable singularities. So we go back to the equation. Basically, the idea is now to build a couple U and gamma such that U solves the constant mean curvature equation on D minus gamma and exactly on D minus gamma. So the constant mean curvature equation cannot be extended to hold to the full D for this particular U we will build. And since you expect to see fractals, it's no surprise that Cantor type constructions pops out. So you do exactly this kind of construction. You start from a Cn, which is the n iteration of a Cantor type construction. You consider Sn, which is the staircase Cantor function. And then you consider this integration, this particular integration, so you can do it by hand. And then you verify that this function satisfies the constant mean curvature equation on D minus Cn. And it satisfies it just on D minus Cn. Okay, so indeed, if you look at the picture, this is a circular arc, here the equation breaks. This is a circular arc, here the equation breaks, and so on. Moreover, it's actually easy to show that this is regular in this sense for any n. Then you take the intersection of all the possible Cn, so you get gamma, and you show that this function un are converging to some u. Now, two things needs to be observed. The first is that the Hausdorff dimension of the gamma obtained in this way can be made alpha by just playing with the Cantor construction. So if instead of removing 1/3 from the middle interval, you remove, let's say, 1 minus tau, with tau between 0 and 1. If you change tau, or something like that, if you change the sides of the central interval you are removing, you change the Hausdorff dimension of the limiting set. So you can get all the alpha between 0 and 1. Other important fact, the alpha Hausdorff measure of this gamma will be positive, strictly positive, non-zero. Otherwise, I could invoke Pokrovsky's theorem. It will be strictly positive. And this function u obtained as the limit of this un will solve the constant mean curvature equation just on 0, 1 minus gamma. Okay, this comes from the good convergence, so the regularity is kept. And so you gain yourself this profile. Now, we would like to use this profile to basically glue it together in several directions to basically close it and make it a closed set so that we can say that we have a Cheeger set. If you wonder yourself how this, the iteration goes, here's a picture. So this is the second iteration. So the constant mean curvature equation holds just here. Then this is the third iteration, where the constant mean curvature equation holds here, here, and here, and it breaks here. Then while you go on, the part where the constant mean curvature equation fails, it becomes dusty and more dusty. So here it's smaller, and then it gets even smaller. So it's becoming a fractal. Okay, so how do we build how do we put the last piece together? This is how it looks like. Sorry. Some water. Okay, this is how it looks like. So the final piece we need is to glue it together. So the red guy is the profiled obtained by this iterative procedure. Now you place it one in this direction, then you place it one in this direction, then you place it one in this direction, and then one in this direction. Then you have to link them, and you use this circular arc, which spans an angle of sides pi over 2, and do not affect the regularity, because this profile has also the good taste to have zero derivative on the left and on the right. So when you glue it with the circular arc here, you don't break basically the C1 regularity too much. So it's going to glue very well. Okay, so with this gluing procedure, we have built the red set. But we need this red set to be a Cheeger set of somebody, because otherwise this won't be any kind of example. Now recall that the free boundary, whatever you do, the free boundary will need to have constant mean curvature. So the only part with constant mean curvature here are this part here, where the equation still holds. Okay, of course, these arcs is artificial, and it has the same radius than this other one, so it's 1 over h. So the constant mean curvature condition here tells you that this part will be free boundary. So if we go back to this graph, so I can, just by looking at the graph, I can tell you that this will be free boundary, and this guy here will have to be contact surface. So you need to have so what you do, you basically build the omega around in a way that it lifts where you have constant mean curvature, so where the equation is satisfied, and then it sticks on the counterfractal part. Okay, so you can build a family of this omega black here. Now you have to ensure that you can find at least one such that this red guy is a Cheeger set of this omega. To do that, and that's why we are stuck in planar dimension, to do that, we had to employ these two instruments here, which are available just in the plane. So up to the best of my knowledge so far, I don't know any instrument, technical instrument like these two, which works in bigger dimension and which are important to basically establish this equality. Okay, so because you have built E, you have built omega, and then you want to say that actually E and omega are linked by this relation. So these two instruments basically gives you a list of conditions that needs to be verified so that E is a Cheeger set of omega. Perfect. So, but we have it in the plane, so you can run this argument in the plane, and you can prove that the set E you've built is the Cheeger set of this omega out there. Very good, and so you're good to go. So let's do some final consideration. So the first naive one is, are these bounds sharp also in dimension bigger than 3? As I said, the construction of the counterexample fails, but it fails for two reasons. The first is that you need to understand a little deeper the existence of couple U gamma, where U is a solution on D minus gamma, and gamma is big in some sense. And so they also need to have the required geometry to be surgered together as we did in the planar case. Then the second thing which is missed is that you want to have an instrument to, once you build E, once you build omega around E, to guarantee that E is a Cheeger set of omega. Okay. Now, the last two observations are more like philosophical, but even if, okay, the last one is a question I would like to leave, the C and as well as the A. The B is more a remark. So this whole argument is sensible to the regularity of the boundary of E. So our statement was, the boundary of omega C1 alpha implies HD minus 2 plus alpha positive. Or actually, you can change this statement in saying that if boundary of E is C1 alpha, then HD minus 2 plus alpha of boundary of E intersected boundary of omega is positive. So in particular, being sensitive more to the regularity of the boundary of E means that if you start from a convex set, you immediately deduce that the boundary of E is C1 1, so you can run the whole argument with alpha equal to 1. So you get this condition not only for C1 1 sets, but also for convex sets. And the last thing about convex sets, and then I'll stop, is the following one. Now, I told you that the bounds of our theorem were global and not local, because you can always cook up this counterexample where you push inside omega and you make it touch the boundary of E in a weird way. But if you are convex, you don't expect, if you are convex, you cannot do that. So you don't expect this kind of behavior somehow. So what you think is that the bounds for the convex set, so these things happen also at the local scale. In particular, what you expect is that if you look what happened inside the small open set A, either you see contact surface, a positive measured contact surface, or you see nothing. Okay, I've concluded. I've said all I was planning to say, and I hope it was clear, and I thank you very much for the invitation and for all the attention.
Thank you very